This is the third video for Introduction to Solutions. In this final video, I want to finish off concentration determination of a solution. We're going to look at mass percent, which is a third way of expressing solution concentration, and then we're going to look at solubility curves. Okay, so we've already discussed molarity and molality. Now let's look at mass percent. Mass percent is simply just what its title is. You want the mass of the solute, okay, so the dissolving medium, so this might be in grams, and we're going to divide that by the mass of the total solution. So the mass of the total solution is going to be the mass of the solute plus the mass of the solvent, okay, those two together. Okay, so mass of solute divided by the mass of the total solution. And then we're multiplying by 100% just so that we can have that percentage marker. Okay, so let's try an example here. Okay, we've got determine the mass percent of solution if 1.5 moles of sodium chloride are dissolved in 1.1 liters of water, and the density of water is 1 gram per milliliter. Okay, so we have the solute is going to be this sodium chloride, so let's take that 1.5 moles of sodium chloride and let's change that to grams. So we need our molar mass. Okay, and we did this in an earlier example, 58.45 grams. Okay, that's your molar mass. So we solve this. Now this is going to be the mass of the solute. So 1.5 times 58.45, that comes out to be 87.675 grams. Okay, I'm carrying some extra sig figs here because I don't want to round until the very last step. Okay, that's going to go right here. Okay, now let's take the 1.1 liters of water, and the density was given because we need to change that to grams. So we have 1 liter is equal to 1,000 milliliters, and then we know that 1 milliliter is 1 gram. And see, these cancel, milliliters cancel. So we have a total of 1,100 grams of water. Now our total mass, let's just add these together. Okay, so we have 1,187.675. Now remember, I'm carrying some extra sig figs because I don't want to round off until the very end. Okay, and that's your total mass. Okay, so now the mass percent is going to be equal to the 87.675 divided by the 1,187.675. Then we're going to just multiply by 100 for the percentage marker, or if you like, just move the decimal 2 places to the right. That works just as well. So when we do this, we get something like 7.3820, and it just keeps going and going with decimal placeholders. But let's go back and look at our sig figs. So this right here was 2 sig figs, and this was 2 sig figs. So let's take this final answer and let's just make it 2 sig figs. Let's make it 7.4%. Okay, and that is our mass percent. Okay, so mass percent, we take the mass of the solute, how many grams of solute, we divide it by our total mass of solute and solvent. And we'll often have to incorporate this density of water, 1.0 grams per milliliter, into that, since many of our solutions are aqueous or water-based as the solvent. Okay, so that's mass percent. You see this kind of percentage expressed on a lot of consumer products. Rubbing alcohol, hydrogen peroxide, you'll see percentage values on those. So you see that quite often. Okay, now let's look at one other thing before we wrap up solutions. So let's look at solubility curves. Okay, with solubility curves, what we have here is we have the solubility of a substance. Okay, each one of these lines represents a different compound, you can see. So how much dissolves in 100 grams of water, water being the solvent, at various temperatures. Okay, see, like for instance right here, the ammonia at 90 degrees Celsius, we can get about 10 grams to dissolve in every 100 grams of water. And remember, 100 grams of water is 100 milliliters, so if that helps you relate that to. Or here's table salt right here, and notice its line goes across. It's almost uniform straight across there. And see, there's very little increase in solubility as temperature goes by. And but we can see at various temperatures what the solubility is in every 100 milliliters or 100 grams of water. Okay. Another common compound, potassium chloride, you can see a steady increase in solubility as temperature increases. Okay. And notice that most of these lines have a positive slope, meaning that solubility increases as temperature increases. But notice that, for example, the SO2 and the NH3, those have negative slopes, as does the HCl. Okay, so what do we know about those compounds? Those compounds at room temperature, okay, and at all of these various temperatures, okay, we know that those compounds exist as gases. Okay, those are gases. And remember on a previous discussion of solutions that with gases, as you increase the temperature, the solubility decreases. Okay, remember the idea of dissolved oxygen and keeping your aquarium fish alive. If the water gets too warm, the dissolved oxygen level decreases and your fish suffocate. Okay, so these with the negative slope, we see those are gases. So with an increase in temperature, we get a decrease in solubility. Okay. Now, I want to break out one particular line here, and let's focus in on it for an example and to learn three new terms. Okay, three new terms that go along with solutions. Okay, so let's focus in on this sodium nitrate line here. Okay, solubility curves helps us determine when a solution is saturated, unsaturated, or supersaturated. Okay, so three new terms: saturated, unsaturated, or supersaturated. Okay, so let's go right up here to 30 degrees. And sodium nitrate has a solubility of, let's say, 97. That's about 97 grams per 100 milliliters of solution. At this point, that is the maximum amount of solute, sodium nitrate, that can be dissolved at this particular temperature. Okay, that is what we term a saturated solution, meaning any more at that temperature that is attempted to dissolve, it won't. It'll settle on the bottom. So it's a saturated, okay, saturated solution, the maximum amount that can be dissolved at a given temperature. Okay. Now let's say we were making this solution of sodium nitrate and we warmed the water to 30 degrees and we start stirring in the sodium nitrate, and we only stir in 80 grams of the compound. Okay. So 80 grams, even though it can dissolve 97 at that temperature. This resulting solution would be called unsaturated, or termed as an unsaturated solution. It has a smaller amount or a lesser amount than what actually can be dissolved. Okay, some people might term it to be a dilute solution. You might have heard that before. It's dilute, or some people use the phrase weak, but that's not an appropriate use of that term in this case. But this is an unsaturated solution when you dissolve a given amount of solute that is less than the maximum that can be dissolved at that temperature. Okay, so that would be unsaturated. Okay, notice that we're below the curve. The line here is the saturation line. If you're below it, you're unsaturated. Now, a third scenario we can have is what we call supersaturated. Okay, a supersaturated solution is where we dissolve a certain amount of solute. Okay, we make us a saturated solution. So we warm our water to 30 degrees. We dissolve the 97 grams. Okay, we make a saturated solution. Then we turn the hot plate off, and the water in our solution begins to cool down. So it slowly cools down, and let's say 10 minutes later, the water is now, the solution, instead of being 30 degrees, it is 20 degrees because it just naturally cools down like a cup of coffee or hot chocolate cools down. As it cools down, if you let it stay calm, okay, meaning don't stir the solution, don't shake it, just leave it undisturbed, oftentimes that 97 grams will stay in solution because it doesn't have a seating site, a site to crystallize. Okay, so what we would notice then is that we would have a 97 gram amount dissolved, but our water, our solution, has cooled to 20 degrees. So our data point now, if you notice, is above the saturation line. That would result in what we call a supersaturated. Okay, supersaturated solution. It's above the saturation line. Okay, it's above this saturation line. So we call it supersaturated. Now, the perfect example for supersaturated solutions, if at Christmas or at holidays, you and your family make a traditional hard candy, okay, like Jawbreakers or Jolly Rancher kind of candies or lollipop style candies, that hard candy, you are actually making a supersaturated solution, and it's seeding, it's crystallizing on you and into that hardened candy. Okay, if you make a solution and you get it saturated at a particular temperature, it's saturated, and then you slowly cool it down, you can have those solutions stay, saturated. But now, see, because you're above this point, you're considered supersaturated. And when you disturb it, you can shake it, you can try to stir it, all of a sudden all of these crystals will appear and the solution will solidify. It's called supersaturation, and we see that with a lot of hard candies. You will see that happen. If you get on YouTube and you type in supersaturated solutions, the crystallization of one, you can see some examples of an aqueous solution just turning solid. It looks like it's freezing, and but that is where you have more than the saturated amount dissolved at a particular temperature. So we have unsaturated, that is below the saturation line. Saturated is on that curved line, and then supersaturated is above. Okay.